In this video, we'll learn how to use the Pythagorean theorem to solve problems involving right triangles. A right triangle is a triangle that has a 90-degree angle, and it has a side opposite the right angle, which is always the longest side. It's called the hypotenuse. That's a y. And the other two sides that come together to make the right angle are called the legs. Typically, the hypotenuse is identified with the letter C, and legs are A and B. The theorem says that if you take the length of the legs and take them to the second power and add them together, that will always equal the square of the hypotenuse. I'm going to show you not a formal proof of the theorem. It's sort of a, intuitive. You can see that it works. And this is going to take me a little while to do this screen, so be patient with it. Draw a right triangle. I'm going to say this is side 3, 4 units, and 5 units. Then I'm going to make a square that'll have lengths 4, and of course that square will have 16 smaller squares, and it'll be comprised of 16 square units. Then I'm going to make a square that has sides of 3, and that would be 9 square units. Then I'm going to go opposite the right triangle and go make it a 5 by 5. And this is where it gets a little tricky to try to guess where these would come in. Somewhere like this. And obviously my drawing's not terrific because these little squares here should all be the same size on each of these, and they're not. But just imagine they are. So this is the triangle right here. Not that that part's very important. I just want to kind of shade it in so it highlights the squares that we have here. If I would take the squares from the blue square, this one right here, and rearrange them piece by piece, section by section, like take these 3 and move them up here. So just imagine they're not there anymore. Take these 3, move them here. Now I'm left with 3 more, and take this one right here and put it here. Take these 2 and put them here. I get a square that is a 5 by 5. Matching this 5 by 5, which goes to just demonstrate that a squared, which is this one right here, because but call this A, by the way, and call this B, and call this C, a leg, and hypotenuse, that a squared plus b squared equals c squared, or 3 squared plus 4 squared equals 5 squared, because the square is the same size as the square that I constructed when I took the 3 by 3 and the 4 by 4 and kind of combined their parts. That wasn't a real formal proof, not a real formal proof of the theorem, but kind of see how it would work. So how does this work if I know the length of the legs? So if I knew I had, say, an 8 unit by 9 unit, so this is a side A, it's like side A, like side B, then the hypotenuse, which should be side C. The theorem says that a squared, or 8 units squared, plus 9 units squared will equal c squared. When I do 8 times 8, I get 64. And units times units would be square units, and that's kind of important to keep in mind that this is really 64 square units, plus 9 times 9, 81 square units, equals c squared. These add up to 145 square units. Units don't change when you add, they do when you multiply. That equals c squared. Then I can use the property of equality. It says I can take the square root of everything on each side. I know the square root of 144. 144 is a perfect square. This is actually going to be slightly more than 144. This is where you probably would punch it in on a calculator, and I think it comes out to be 12.04 units equals c. When you take the square root of u squared, that's u. So we come back to how long is this, and it would be approximately 12.04 units, not square units. Because I'm keeping track of how the labels work. And if we knew, this is a little more difficult problem, not much. If we knew a leg, let's say this leg is 7, and we don't know this one, but we know the hypotenuse, and we'll say units, it's 10 units. So then when we have the theorem, we could say we know, it really doesn't matter whether you call this A or call this side A, but just so you know, A is typically a leg and B is a leg, and then this would be C. So the theorem would say 7 squared, 7 units squared. I should put that, maybe a little more careful how I do that. 7 units squared plus B squared equals 10, to 10 units squared. So this would be 49, 7 times 7, 7 units times 49. 7 units times 7 units is 49 square units, plus b squared equals 100 square units. Subtract 49 from both sides. You get b squared. I'm going to slide over to the left a little bit because I'm running out of room there. Equals 51 square units. Take the square root of both of those. The square root of 49 is 7, so the square root of 51 is slightly more than that. It would actually come out to be approximately 7.1. And again, it's units. There's a special ratio in right triangles called the 3-4-5 ratio. Carpenters use it all the time. People that want to construct something where two sides come together to form a right angle will use the 3-4-5 ratio. It just, if you have a right triangle and one leg is 3 and another leg is 4, you can be sure that the hypotenuse is 5. So this could be 30, 40, 50. Or if you have the 3, 4 to 5, you can use any scale factor that you want to. That is, multiply by 3, 4, and 5 by any whole number. For instance, you could take 2, just double the 3, double the 4, and double the 5. Or start with 3, 4, 5, and you could multiply them by 2.5 if you wanted to. And, well, I wasn't prepared to do the math, so I'll try really quick. 2.5 times 3 would be 7.5. 2.5 times 4 is 10. That's an easier one. 2.5 times 5 is 12.5. I think I'm right on that. You can check and verify it. I might have made a arithmetic mistake there. You can multiply them by 1,000 if you wanted to. If you had a right triangle, it would be that had the 3-4-5 ratio. It would be one of the legs would be 3,000, one would be 4,000, and the third would be the hypotenuse, always the longest side, would be 5,000. So that 3-4-5 is a special ratio.